Good evening, Pittsburgh. I'm Michael Clark of the Action 4 News Team. Today's big story is on styrene. You know what it is. It's in your packing peanuts, your cafeteria trays, and most importantly, the coffee that allows you to stay up late night studying. There are two main ways to produce styrene, one of which is the dehydration of ethylbenzene, as well as the oxidative dehydration of ethylbenzene, the former of which is the most commonly used in industry today and accounts for 85% of all styrene. For more on this, we go to our Washington correspondent, David G.
Thank you, Mike. So, as Mike just explained, dehydrogenization is the most common way to produce styrene. But before producing styrene, we need to create ethylbenzene. And we create ethylbenzene by alkalizing benzene with ethylene. And when ethylbenzene is produced, we add it along with the steam to produce styrene. And hydrogen, carbon dioxide, and toluene and benzene are also produced as byproducts, and benzene are recycled again after alkalizing it again with ethylene. And this whole process is very endothermic because it only occurs at an equilibrium point. So to reach this equilibrium point, about 117 kilojoules per mole of superheated steam is added. And after styrene is produced, it needs to be cooled down, and when it needs to be heated up again to recycle benzene and unreacted ethylbenzene, it, it needs a lot of heat. So because of that, it makes this whole process very highly endothermic. And to keep to keep its temperature to keep its temperature high enough, we often use diluted steam to do that. And we also use potassium catalyst to facilitate this whole process. And but this potassium catalyst only lasts about 2 years, and it can often deactivate before 2 years. And when it deactivates, its potassium migrates to the cooler region or the center of the catalyst. So it actually when the potassium catalyst deactivates, it actually lowers the rate from ethylbenzene to styrene lower, and so even the selectivity lower. So catalyst can be good if it's not deactivated, but then it's usually good when it's activated. And thank you.
Thank you, David, for that very interesting and informative report. Next up on our journey through styrene, we will consider the oxidative dehydrogenation of ethylbenzene. And for this report, we'll go to our very own Bill Dollinick.
Thank you, Michael. As Michael had said, oxidative dehydrogenation is another common process in creating styrene in the industry. It is a exothermic reaction which requires less superheated steam to be added to the reaction. This is one of the advantages when using oxidative dehydrogenation. The actual comparison is a 1 to 5 ratio of superheated steam to hydrocarbon for oxidative dehydrogenation, whereas when compared with the actual dehydrogenation process, it is a 7 to 12 ratio. Another advantage of the oxidative dehydrogenation is we can actually achieve higher selectivity and higher conversion rates using different catalysts in this reaction. We can actually achieve a selectivity of over 90%, whereas dehydrogenation process can only achieve a selectivity of 90% max. And also, the conversion rate can be improved to almost 80% or even higher with some catalysts, whereas the conversion rate for dehydrogenation is only at 65%. The disadvantages, however, for oxidative dehydrogenation are that the oxygen provides a combustible reaction, and therefore it is flammable. It makes a flammable mixture, a flammable stream, and is uh, it is a disadvantage when putting this in a process plant. Also, to achieve these higher selectivities and conversion rates, we need to add a high amount of oxygen, which increases this danger to flammability. All right, back to you, Mike.
Thank you, Bill, for that delightful story. Wait, what's this? We have breaking news, this just in, of brand new technologies on the styrene scene. We go to Channel 4's own Xiang Guo reporting.
Thank you, Michael. So just as Michael mentioned, membrane technology has been widely used in order to modify the producing process of styrene. So let me introduce how it works now. For the dehydrogenation process, it removes the hydrogen from the produced stream. And for the oxidative dehydrogenation process, it enables the oxygen to diffuse selectively through the membrane to react with hydrogen or directly with the hydrogen carbon on the other side of the membrane reactor. So in this case, there are several advantages of this membrane technology. For the dehydrogenation process, since we remove the hydrogen from the reaction, it shifts the direction of the equilibrium to increase the yield of the styrene. For the oxidative process, since we just allows this reaction to occur without mixing oxygen and the hydrocarbon, we can minimize the undesired oxygen insertion reaction. Whoa, looks great! And besides that, there are two different configurations for the membrane reactor, CMR and IMCR. Normally, we apply the CMR to the dehydrogenation process, and we apply the IMCR to the other one. Of course, there are different materials of membrane itself. There are two main types, porous and non-porous. As far as dehydrogenation process is concerned, we normally use the porous membrane in order to reach a high efficiency to produce styrene. So that's all. Thanks, Michael.
Thank you, Xiang. That story really blew my membrane. After considering all of the facts brought to us by our hard-hitting journalists, we at the Channel 4 News team believe that the dehydrogenation of ethylbenzene is the most efficient process to produce styrene. We believe this because it is a process that has been used for over 100 years and yet still today produces 85% of the world's styrene. While oxidative dehydrogenation may perhaps be more efficient in theory, it does have many safety and financial concerns. Also, we learned from Xiang that the membrane technology, when coupled with the dehydrogenation process, may perhaps be the styrene production method of the future. With that, we leave you. I'm Michael Clark of the Channel 4 News team. You stay classy, Pittsburgh.